Well, let me see if I can remember what all these panels are here. This is a plot that shows the total rate of working of astronomical forces on the ocean. This is a plot that shows the rate of working of the self-gravitational force of the tide on itself, which is a tiny thing, and indeed the color bar here is only 1/10 the size of this color bar. This is the rate of mechanical working on the ocean tide caused by the body tide, so it's kind of a flux from the sea floor to the tide. And this is the same thing from the load tide, which is a lot smaller. So the color bar is a lot smaller than this one. So you take these four things here, those four panels, you add them together, that's the total rate of working on the ocean tide. We want to subtract off the flux divergence from those currents, that's this. So the dissipation is the difference between these two panels, and you can immediately see a problem. Those two panels look almost exactly alike, so you're looking for a small difference in two big numbers, so the result's going to be noisy. And it also means that you have to do things like this subtle self-attraction force. You want to do that as rigorously as possible because you want these two things to be as accurate as possible when you subtract them. When you subtract them, you get something like that. And I don't think there should be any negatives here, so when you see blues, I think that tells you something like the noise level of this. But overall, where you see red, that's where dissipation's occurring. There's lots of dissipation in the shallow seas, Patagonian Shelf, European Shelf, but there's also dissipation out in the open ocean, like the Hawaiian Ridge, South Atlantic, Mariana Trench, things like that. If you sum up all these, integrate them all, you get a deep water dissipation of 700 gigawatts and shallow 1,700 gigawatts. This is M2 only. So in the deep, for all constituents, you want to multiply this by 1.5, so that gives you about a terawatt. So most of the dissipation is indeed in the shallow seas. So Harold Jeffreys was 2/3 right. He wasn't completely right, he was 2/3 right. But you still have this 1/3 that's out in the deep ocean. And for all constituents, it's about a terawatt. So the rest of my talk now is about what are the implications of this 1 terawatt of dissipation out in the open ocean. The first thing you can say is the mechanism involved must be conversion into baroclinic motion. If you look what tidal friction or bottom friction is out in the deep water, it's just minuscule. So the only mechanism you can have is a conversion to internal waves. So then that brings up the next question: what is the ultimate fate of that energy? Which leads to a whole bunch of questions. How much, for instance, when you convert it to baroclinic energy, how much is dissipated locally, directly into turbulence? How much is into internal waves, internal tides? How much into low modes versus high modes? How do the internal tides dissipate? Do they go long distances? Do they dissipate right near the generation source? Depending upon how you answer those questions, you then have possible ties to ocean mixing and the meridional overturning. So I said there's a 1 terawatt of power out there in the deep. Possibly that could go to power the MOC. And if that's important, then you have to worry about how to get tidal mixing into ocean general circulation models. And then if I have time, which I may not, I'll talk about possible hypothetical climate feedbacks between tides and climate. Okay, so I'll go through each of these 5 topics. Oh, here's topic 0, sorry. So, this is trivial almost, but if you have a barotropic ocean tide model, then suddenly you have to change the way you have dissipation in that. You can't just have all the dissipation in the shallow seas anymore. You have to put some out in the open ocean. And there's now sort of a cottage industry. A bunch of papers have been published on how to put open ocean dissipation into a barotropic model. And this is a normal barotropic model with all the dissipation in the shallow seas. And then this is one Steve, Jane, and Lou St. Laurent published, where you can see a lot of dissipation out in the open ocean. If you do that, you suddenly get a model a lot more accurate. Okay, number 1, dissipation goes into baroclinic motion, which means I get to talk about internal tides, which I have to do anyway since Barry's here. Does it seem like 20 years ago?
That was published a month after I arrived here.
Yeah. So let me give you a little background on that. So Gary and I were at a TOPEX science team meeting in Biarritz, on the coast of France, nice place. And instead of being in the auditorium, we were outside in the hallway. And he was showing me some work that he had done on the Hawaiian tide gauges. He was looking at the tide at Hawaii, and he was seeing changes in it over time. And I won't go into why, but it looked like those changes were caused by a surface manifestation of the internal tide being generated at the Hawaiian Ridge, which was cool. And we said, wow, if the effect is so large at those tide gauges of changes in the tide, maybe the part that's unchanging, the constant part of the internal tide, could be seen further offshore, even in altimetry, maybe along the altimeter tracks. Voila, that's what that is. So those are estimates of the M2 tide along TOPEX tracks. That's the amplitude. And then you take those amplitudes and you high-pass filter them to get rid of the broad-scale barotropic tide. And so you have these oscillations. If you look at the wavelengths, they're exactly what theory predicts the wavelength should be for a first mode baroclinic wave at the M2 frequency. Although in a place like right here, you can see half that, that's a mode 2 wave. And if you look at the phases, which I don't show here, they show propagation both north and south of the ridge, away from the ridge. It turns out that these things are all over the ocean. So there's lots of waves being generated at Hawaii, lots in the South Pacific, all through the western Pacific topography. And even out here where the M2 tide is actually fairly weak, you can see these nice wiggles out through there of these things being generated. So you can take data like that and go back to your problem of tidal dissipation to find out what's happening to the internal tide and compute things like these energy fluxes from the internal tide. This is work that David Cartwright and I did 15 years ago now, which showed energy fluxes along the Hawaiian Ridge. That's the Hawaiian Ridge right there. So you have fluxes to the north, fluxes to the south, and also a lot of fluxes being generated up here at the Aleutians and going south. It turns out, in retrospect, this is a lousy map because it's just too overly smooth. And the reason is because it's based upon TOPEX alone, TOPEX alone. If you take a numerical model of the internal tide at Hawaii, it looks something like this background picture right here. And the tracks here are TOPEX tracks alone. So Cartwright and I were trying to compute energy fluxes for that stuff in color based upon only these tracks right here. It's sort of almost, I think if we'd understood what these things look like in reality before we started, we probably wouldn't have tried it. It's a wonder we got anything reasonable. You can see once you add in some more ground tracks, these are tracks from when they moved TOPEX to an interlaced track. And then this is adding in Geosat follow-on, adding in InVSat data. Now, finally, with all these different satellites, maybe you can get the coverage needed if you want to try to map these things empirically. Maybe. But even here you have diamonds like right here. Like this diamond here has an anomaly going through it, but this one doesn't. How do you know without some more ground tracks? Fortunately, we'll get more ground tracks. Sentinel-3 is going up this year. Anyway, taking these multi-satellite tracks now, and this is an example of trying to take tracks from all these different satellites and then just map this internal tide field. This is an example for the Atlantic and the Indian Ocean. You can see all these waves. If I had a movie here, you would see these waves propagating slowly away from the Amazon shelf and off Cape Verde and places. But anyway, you can see these things all over the place. And the character has, I mean, you can look at them and say, wow, that's signal for certain. But in a few other spots, you can look at it and say, wow, that kind of looks like noise up here too. And the reason is because when you get into a spot of high mesoscale variability, like the Agulhas or the Gulf Stream, you have sea level moving around by a meter because of all that mesoscale. We're trying to look in the Topex and JSON data for a signal that's sometimes sub-centimeter. If you got sea level moving around a meter, you just can't pull out this small signal. So this has problems in a few spots near boundary currents. This is an example now of that Zhong Zhao from the University of Washington did. He's done some good work on these altimeter measurements. This is K1 energy fluxes away from Luzon Strait. And you can see great big internal tides, K1 internal tides, being generated there in the strait and propagating both east and west of the strait. The cool thing about this is that the phase velocity of an internal tide depends upon the Coriolis parameter. And so the higher up you go in latitude, the faster the phase velocity is, which means that you get this nice refraction effect on these wave fronts. They just slowly bend around. And that's shown very nicely in this. And remember, this is strictly analysis of the altimeter. There's no numerical model or no ocean model going into this. Okay, so now, the great mystery of ocean mixing. So if you believe the stories that, say, Walter Munk and Carl Wunsch have come up with, the scenario is as follows. You have deep water being formed in the polar regions. That sinks and fills up the ocean bottom. If you did not have ocean mixing, then over time, the ocean basins would simply fill up with cold, stagnant water. You have to have mixing to balance that formation of deep water in the poles. Mixing takes mechanical energy of a certain amount. So what Walter Munk did was compute, based upon the rate of deep water formation in the poles, how much power you have to have in mixing to balance that deep water formation. And he got 2 terawatts. Well, people have looked at the wind fields on the surface of the ocean, either with scatterometer data or numerical weather models, and they think that the winds could come up with maybe a terawatt. But I just showed you in that previous plot of the dissipation that the tides can also come up with a terawatt. The two together come up with Munk's 2 terawatts. So not everybody buys this, but I think right now this is the sort of paradigm of maintenance of the abyssal stratification, that a terawatt's coming from the winds and a terawatt is coming from tides. The terawatt from tides goes first into baroclinic motions and then into turbulence and mixing. This is an example now of just one instance of tidal mixing. It's a spot near the Hawaiian Ridge. Measurements off the Scripps flip instrument. What you see here on each panel is about a day and a half. So you have 3 cycles, basically, of a semidiurnal tide. During neap tide and spring tide, this is a plot of predicted barotropic velocity. And then these are measurements of the velocity at depth over this day and a half during neap tide and spring tide. And then these are 2 different ways that the group at Scripps had to compute turbulent dissipation. I won't go into the details of how they did that, but anyway, you can see in the velocities there are 3 tides, there are 3 tides, and in the turbulent dissipation, not so clearly in the neap tide, but certainly in the spring tide, you see 3 peaks here. So that's tidal mixing in action. This is another example, but I think I'll skip that. If tidal mixing is important, that means that people that run ocean general circulation models have to somehow parameterize that in their models. And there are now a number of models that have tried to do that. I think Steve Janes was one of the first. This was published in 2009, in which he took a standard, I think a fixed diffusivity for the whole global ocean and compared that with one in which he used the dissipation of the barotropic tide to change the diffusivity and to put mixing where the barotropic tide was losing energy through some relation like this, where you have some kind of mixing efficiency, and this E is where the barotropic tide is losing energy, and then this F is where you put the energy within the vertical. And you can see in his results, these are zonal averages of the currents. Things don't change too much 1,000 meters and above, but in the deep ocean, the currents are a lot more intense. So it makes a difference. And like I say, a lot of people have been doing that, but the details really matter. You have to think about all the physical mechanisms going on between getting from the surface tide into internal tides into mixing. And it's more complicated than what Steve Jane did here, where he was looking at just the dissipation in the barotropic tide and putting that energy directly into the ocean at that spot. We know that doesn't happen, for instance, in the internal tide, because I showed you plenty of maps where the internal tide is getting generated at the Hawaiian Ridge, and then that energy is going away. So where it goes into the mixing is anybody's guess. This is a nice diagram that was just published by Amy Waterhouse and a big group, Scripps and some other places, in which she tabulated all the major microstructure experiments that have been done. And for each of these experiments, she computed how much power is going into the ocean from the wind and the tides, and then based upon the microstructure experiments, how much turbulent dissipation is taking place at that spot. So if energy was going into the ocean, and at that spot it was being converted to mixing, then all these experiments would be along this straight line of where x equals y. And there are a few experiments where it seems that's indeed the case. But for most of the experiments, you can see that energy is being dissipated somewhat at that spot, but then it's going away. And so you need to figure out the method that energy is being dissipated and how it is converting to things like enhanced diffusivities. And that is a big problem, and it's an outstanding issue, and I think it's going to be an issue for all these circulation models. How do you parameterize something like this in an ocean circulation model? Okay, so this is an example. This is kind of a bad view graph because it's so complicated, but this is an example of some ocean general circulation models that actually have put tidal forcing in them. There are a few examples like that, people doing that. This is a bad slide because I have two different locations. These locations here are the Hawaiian Ridge. In the North Pacific, these are from the South Pacific. But no mind, this is what the altimeter is telling you is happening in Hawaii, around Hawaii, and this is what the altimeter is tells you is happening in the South Pacific. This is what three circulation models are saying is happening. This is the storm tide model that Malte Mueller, who worked at Hamburg, is running. This is the MIT ECHO model, and then this is the HICOM model that Brian Arbick is running at Stennis. And you can see that, like for the storm tide, either it's not generating enough internal tides there at the ridge, or it's decaying too rapidly. The opposite is happening in ECHO. Either too much energy is being generated, or it's being allowed to propagate too far. So storm tide's too weak, ECHO's too strong, but just right. Goldilocks solution, sort of the HICOM model, at least in an overall general picture. But if you look at the details are a lot different. So you couldn't take a model like this and use it to compute tide corrections for altimetry or anything. But it gives you an idea of what the scales are that it's seeing, that it might be right. So people are going to have to work out all these details in order to parameterize this surface tide to internal tide to turbulent mixing. Okay, I just have a few more slides here. Now, this looks like I'm going off a completely different topic, but it's actually tied in, so bear with me a minute. If you run a tidal model for the present day, and then run that same model for 10,000 years ago and 20,000 years ago, with the seas different because it's the middle of the last ice age, so the Bering Strait is closed off, and some of the European shelves and shelves in there have gone. You can see that the amplitude, this is the amplitude of the M2 tide, the amplitude is a lot larger 20,000 years ago than it was here. This seems to be a robust result. It seems this has been done by a number of different models. Everybody sees that during the last glacial maximum, the tides in the Atlantic were a lot larger than they are now. The Pacific tides didn't change all that much. But the Atlantic tides, which are sort of semi in resonance now anyway, they did change a lot. So if all this story with tides and tidal mixing is true, then it got people to thinking that maybe there are these feedbacks that could occur. You have sea level changing, that changes the tide. The tide changes the stratification because it generates baroclinic motion, and baroclinic motion in turn changes the tide. So you have a feedback right there. Stratification changes climate. As climate changes, it changes stratification. Climate changes, it changes sea level. So you have these loops like this, which are hypothetical. But I'll give you two examples of people thinking about this and working out some scenarios. One is this paper by Carl Wunsch, in which he had speculations on a schematic theory of the Younger Dryas. Now, the Younger Dryas, of course, was that period 12,000 years ago or so, in which you had a gradually warming Earth as you're coming out of the ice ages. But in the Younger Dryas, it suddenly went cold again for a short period, and then it started warming up again. So Carl looked to think, well, could tides be an explanation for this? Could the changes in the tide in the Atlantic cause changes in tidal mixing, which changes the stratification, changes the meridional overturning? Could that be responsible for this? On the surface, it sounds like it's crazy. But in fact, tides does give you a mechanism for a rapid change. Because if you think about coming out of the ice age, sea level is going up, 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 up slowly. But then quite suddenly, sea level breaches the European shelf, suddenly breaches the Patagonian shelf. And so quite suddenly, the ocean tide and the whole Atlantic changes. So if you really do have these mixing scenarios, then conceivably that